All right. So the last thing in this chapter you have to learn is something called inclined plane. Okay. So inclined plane we have not covered yet. That you have to learn. Okay. Now, so far all the problem we solved is basically on horizontal plane. Okay. So a plane, something like uh, I mean, something like this. So we have a plane, something like this, and the object is on top of it. Okay, all the problem was something like this. But now you see that the object on some ramp, something like this. Okay, so we treat this kind of problem little bit differently, and you need to understand how we treat. Okay, so one of the example before I talk about that, before I talk about the inclined plane problem or the details of the inclined plane problem, here is a an example of inclined plane. Okay, so this ramp, so here you see that we have a ramp. Okay, and the object is here. So if you move it up, or if you move on the other direction, okay, then we have to know how we treat this ramp. Okay, how you solve when you have a ramp something like this. Okay, all right. The first thing here you need to understand is that when we have an object, and if this object has mass, there will be a gravitational force. Okay, and gravitational force is always downward. So if I draw the gravitational force, it will be something like this. Okay, always downward. So here you see that. Okay, so I have two arrows actually. Yeah. So yeah, so this is the gravitational force. I mean, which we call mg. Okay. Now there will be another force, right? Because the object is on some surface, there will be normal force. And remember that by normal force, I mean the perpendicular force, right? Perpendicular from the surface. So perpendicular from the surface here, this term will be this one. Okay. So here you see that it is not, so earlier we see, I mean, if we have an object, okay, if we have an object something like this, okay, earlier we see that we have two forces. One is the gravitational force downward, and another is the normal force, which is upward, right? If the object is on some surface, let's say this is the surface, then we have something like this, right? This is mg, and this is the normal force. But now here you see that in this problem, it is a little bit different. So still this is mg. So this still mg, but the normal force is not just opposite to the mg. Okay, so the normal force this time is this one. Okay, all right. So, and there may be some other force, pull force or push force, or the um, the friction force, right? And we already know what friction force, what pull force, what push force. But the very important thing we have to understand here is these two forces, the Fn, the normal force, and mg. Okay, now because we are now dealing with the inclined plane problem, we do not use our usual coordinate system. So remember that we use this coordinate system where the horizontal plane is the x-axis, and vertical plane is the y-axis. Okay, but if we use this usual coordinate system, then you know that it will be difficult to solve an inclined plane problem. Okay, so to make the life a little bit simple, we rotate our coordinate system, we rotate our reference frame. Okay, so something like this. So now our y-axis is just um, perpendicular to the surface inclined plane, and the x-axis is parallel to the um, inclined plane. Okay, so if we can do that, then the problem is basically solved. Okay, so only one thing here we are doing differently is this one. Our coordinate system is now rotated coordinate system. Y-axis is this one and x-axis is this one. Okay, so x-axis is parallel to the inclined ramp or inclined plane and y-axis is perpendicular. Okay, now the good thing is then you know that Fn is still along the y-axis. Okay, if there is friction it will be in this direction, so the friction will be in this direction, but here you see that the gravitational force mg is neither along the x or y-axis. Okay, so if I extend the y-axis it will be something like this, right? So you see that this force Fg is neither along the x nor along the y-axis, right? So what is the solution then? We already know what the solution, right? The solution is we have to break it. So when there is a force and if that force is not along the x or y axis, we have to break this force. Okay, so here we have to break this force. Now, if this angle is theta, you can show that this angle is also theta. Okay, then if you break it, okay, so follow the exact same rule what we are using so far. We'll have um, this arrow, I mean, this is the x component and this will be the y component. Okay, so why they are x and y? This is x, so this is x component because it is parallel to the x-axis, so it is little bit different. So earlier we see that opposite component is the y component, but here because this is parallel to the x component, this is our x component and this is our y component. Okay, so x component and it will be mg sine theta. Why it is mg sine theta? Because it is opposite of theta, and this will be mg cosine theta. Okay, so we are using exactly the same thing what we are using earlier. Okay, while we break a vector. Okay, and then you just use the trigonometry to know what is the equation. So for x component this time it will be mg sine theta because it is opposite of theta, and the y component is mg cosine theta because that is the adjacent. Okay, and if the object is moving downward, so here you see that the motion is downward, so the friction will be upward, so this is the friction. Okay, so let's see another example here. So here, so this is the normal force, and or Fn is both the normal force, and then here you see that the gravitational force should be perpendicular, should be parallel to this line. Okay, and this will be our y-axis, and this will be our x-axis. Okay, now you see that this one mg is not along the x or y, so you have to break it. So if this angle is theta, this angle will be theta, then this will be mg sine theta, right? And this will be mg cosine theta. Okay, so this is along the x-axis, so here you see that this and that is the same thing, and the friction force will be opposite of the motion. Okay, so that's basically you need to understand to solve an inclined plane problem. Okay, so yeah, spend some time on that, and if you have any question let me know. Now let me solve a problem. Okay, okay, so problem, okay, so I have to erase all these. All right, so I'm going to skip this problem. This is a little bit difficult, so skip it, but don't skip this problem, the last problem. Okay, so here you see that we have a snowboarder. Okay, so this person uh, so slides downward on an inclined plane. So here you see that the inclined plane um, angle is 13 degree. Okay, so here you also see that. And the coefficient of kinetic friction is also given, this one. What is the acceleration of the snowboarder? So we have to calculate what is the acceleration. Okay, so because this person is moving downward, if there is some acceleration, it will be downward. So we, from our common sense, we have to understand this. Okay, now we have to, I mean, yeah, similar to all other problem, all other force related problem, if we have this kind of problem, the first thing we have to do is to draw the free body diagram. That means what are the forces that are acting on this person. Okay, so let's draw. So the first one will be the gravitational force, and gravitational force is directly downward. So this one is the gravitational force. There will be normal force. Normal force is perpendicular to the plane, so it will be in this direction, right? And the person is moving in this direction. If there is a friction force, it will be in this direction, right? So this is the friction force. So let me write down one by one. So this is mg, this is Fn, okay, and this is kinetic friction. Because the person is moving, so the friction will be kinetic friction. Okay, and because the person is moving downward, the acceleration will be in this direction already given. Okay, now we have to choose our coordinate system, right? So remember that whenever an object or a person is on an inclined plane, then our coordinate system is a little bit different. Okay, so our coordinate system, our x-axis, I mean the y-axis will be this one. So this will be y-axis, and this will be our x-axis. I mean, the parallel to this plane will be our x-axis. Now, let's think that this is our x-axis. Okay, so the positive x is in this direction. Okay. Now, this creates a problem. The problem is mg is neither along the y nor along the x-axis. Okay, but we know how to do, right? How to solve this kind of problem. We have to break mg into its y and x component. Okay, now let's try. So the y component will be this one. Okay, and then x component will be this one. Okay, so we already see that. Okay, now we know that this is theta. Okay, so if this is theta, this will be mg sine theta, and this will be mg cosine theta, right? So here you see that this is parallel to the x-axis, so this is the x component, and this is opposite of the y-axis, so this is y component. Okay, so that basically what we need to understand. Okay, now similar to what we did earlier, we have to use the x and y equation. So first let's use the y equation. Fy equal to may. Okay, and you know that there is no acceleration along the y-axis. The person is moving along the x-axis, right? So the right hand side will be 0. Okay, so Fy equal to 0. But what we have in the y-axis, we have positive Fn, okay, and negative mg cosine theta, that is equal to 0. So this tells us that Fn this time is equal to mg cosine theta. Okay, now the person's okay, so just let's keep it, and then we need to substitute this equation somewhere. And we cannot calculate it numerically because the person's mass we do not know. Okay, we know the gravitational acceleration, we know theta, but we do not know the person's mass, so we cannot solve this, okay, right now. Then what is the kinetic friction? So let's then calculate the kinetic friction. Kinetic friction will be this one, Fr K, and it is mu K Fn, right? And this is basically mu K mg cosine theta. Okay. Now we can use the x-axis. Fx equal to, x-axis equation, max. So here you see that this is our positive x and opposite of this is negative x. That means this is negative x and this is positive x. Right? So this is positive x, this is negative x. So in the positive x direction, we have mg sine theta. You see that the direction of this one is along the positive x. Okay. In the negative direction, we have frk. And a is also in the positive direction, so this sign would be positive. Okay. Okay. Now let's then solve for a. So a will be mg sine theta minus frk over m. Okay. Now let's substitute the friction force. So friction force is mu k mg cosine theta over m. Okay. So you see that m is common in all the terms, so you can cancel m. Okay. So m and m cancel out. So the equation we have here is basically this one, g sine theta minus mu k g cosine theta. Okay, here you know everything. You know the gravitational acceleration, you know theta is 13 degree, and you know also mu k is equal to 0.2. So if you plug all these values correctly, the acceleration of this person will be equal to 0.29. So check that whether you get 0.29 meter per second square. So if you get this, then you are done. Okay, so that's basically it. In the next class, I will be talking about the uniform circular motion. Okay, and some part of the uniform circular motion is basically very important. Those who will be designing the highway or some street. Okay. All right. So that's it for today. I will see you in the next class on Tuesday.